Morning, calculus students, or afternoon whenever you happen to watch this, but it's morning for me. Today we're going to talk about our third topic in Unit 1, limits. We're going to discuss continuity and intermediate value theorem. So today we will discuss continuity and develop properties of continuous curves. So that warm up, how would you describe a continuous graph? So kind of ask yourself, how would you describe a graph that's considered continuous? What does it mean to be continuous? I'm thinking that it means to go on forever and ever and ever with no breaks. There are no breaks, there are no jumps. And we're going to talk today specifically about what that means to be a break or a jump. So continuity, and I'm not exactly sure how you want to write that, you can put that in your own words, is a curve or a function. My pencil's not working here. Hold please, technical difficulties. Continuity means to continue. Can't really use the word continue. A curve or a function with no breaks or gaps. Oh goodness, I keep writing up this morning. Or gaps. This is a definition for continuous function as opposed to continuity, but go with it, it's okay. A discontinuity is a break or a gap in a function. So in pre-calculus, you've already seen these. I don't know how much you use the word continuity, discontinuity, especially with piecewise functions. You had functions that were discontinuous at some place. So a continuous function has no breaks. Breaks are caused by two things. Two main things cause breaks. One is the function is undefined. Zoom in here a little bit. F of x is undefined. Or the second thing is the limit as x approaches c of f of x does not exist. And in fact, I'm going to go back to my first one where it has a breaks. Not that just f of x is undefined, but that it's undefined at a particular point. So I'm going to say at c. And when we use c, that just means a particular x value. So x equals 2, x equals 7.5. C is a particular x value where x refers to the unknown, and we don't know what it is yet. So a limit is continuous if each condition is satisfied. So what does it mean to be continuous? So here's the math definition. That f of c exists, or is defined probably, that the limit as x approaches c of f of x exists. So not only does the function exist and the limit exist, but here's the big one. This is the key that you need. That f of c, the function, is equal to the value of the limit. You can't have, your curve coming through here and then a closed circle up here. That would not be continuous because the limit down here doesn't equal the value of the function. If I draw that here instead of using my hands. So here's a line, open circle. Let's say my limit as x approaches 2 is 1, which it would be on this graph. But if I have a closed circle all the way up here, the value of the function is different. So this is how we get a discontinuity. If we wanted those to be the same, this particular point right here would have to be down where the 2 is. So let's see what's going to happen with these. If one of these fails, then there's a discontinuity. So if any one of those things fails, if f of c is not defined, if the limit does not exist or if those two things are not equal, you have a discontinuity. So we have a couple different types of discontinuities, and for me, it's easiest to just look at them. A removable discontinuity is kind of the one that I showed up above. So here's my curve, just making something up here. That could be a removable discontinuity. I'm gonna make another one over here. And here's a closed circle. Either one of these are considered removable discontinuities. The reason being, all you would have to do is put a point at that open circle and you would fix the problem. You would have to move this point up and you would fix the problem. So those are considered removable discontinuities. A jump discontinuity is a little bit different. This is where I've seen with the piecewise functions a lot. Maybe it looks something like this. You have this big gap between one side and the other. That's a jump discontinuity. So one point isn't gonna fix it. And then finally over here, an infinite discontinuity. It's exactly what it sounds like. It's headed to infinity. So my curve is going up. Maybe this side's going up. Maybe it looks something like this. Basically, you're reaching some kind of asymptote. My highlighter's a little thick for that, but there's some kind of asymptote. So on this first one, we're going up to negative or to positive infinity on the left, positive infinity on the right. This one's going down to negative infinity. This one's going up to positive infinity. That's an infinite discontinuity. So that jump is there, but it continues forever and ever and ever. So determine if the following functions are continuous at x equals 2. Well, in order to try that, you want to substitute a 2. So let's find f of 2 equals, well, let's put the 2 in. 2 squared minus 4 over 2 minus 2. Well, f of 2 is 4 minus 4 over 2 minus 2. This leaves us with 0 over 0. Now, 0 over 0 is that kind of weird thing. We can't say that it's 0. I know there's a 0 in the numerator. You can't call it undefined. There's a 0 in the denominator. And it kind of feels like it could be a 1 because the numerator and denominator are the same, but it's not a 1. It's not any of those things. This is indeterminate. You are going to hear that word a lot in this unit, indeterminate. We don't know what it is. But the question at the hand is the following function continuous at x equals 2? The answer is no. It's not continuous. 0 over 0 is not a number. We don't know what it is. There's some kind of hole in the graph. But if I come over here and look at the second one, I have this piecewise function. So this first piece, I know matches the example on the left. This piece is 0 over 0 at 2, but everywhere else it exists. And so if you put any other number other than a 2 in there, you're going to be okay, no problem. And then at 4, what's going on with it? Well, I have x equals 2, so that y value is 4. The best thing to do with this one is actually graph it. So I don't have this set up on Desmos yet. I'm going to pop over to Desmos. I don't know what I have left in here. Y equals, let's do it this way, x squared minus 4 over x minus 2. I think it looked like that. Okay. So there's our graph. It's a little unexpected. It's a line. It's a line, and if you look at it, it's got a slope of 1, it has a y-intercept of 2. That's not actually what I would expect. Now, I actually like this graph better on your TI 83s and 84s because if you do zoom decimal, and I don't have my simulator on my computer right now, but if you do zoom decimal, you will actually see a little gap in the graph. There's a missing piece, a missing pixel. It's zoom number 4, I think. Now, if I take this one and I just try to follow a point along my line, watch those values, 1.7, getting closer, getting closer, getting closer, getting closer. 2 undefined, there's my open circle. It doesn't exist when x equals 2. However, my finger moved. However, what should that y value be? Well, according to the graph, that y value should be 4. So this is looking at those graphical limits like we did yesterday. So yeah, this one's continuous. Go back to my notes. This is continuous. So by graph, I'm going to say yes. Now, do you have to graph all of these? No, there's some algebra that we're going to show you. We're just not there yet. So when I look at that graph, yeah, it's continuous at x equals 4. I think I have a few things to talk about with discontinuities. Yeah, there we go. Now, what kind of discontinuity do we have? There's that piecewise function that I mentioned. So describe the continuity of f of x. You could graph them. You can also test values. The first thing you gotta do is check to see that each piece itself is continuous, and then you wanna see what happens when they meet. So x, that's just a line, slope of 1, slope-intercept of 0, that's continuous everywhere. 3 is a horizontal line, that's continuous everywhere. 2x minus 3, also continuous everywhere, also a line. So everything looks good there. But you wanna try the values at those points where they meet. So at x equals 1, we're going to check it out, and x equals 3, we're going to check it out. So f of 1 no more technical difficulties this morning. All right, I'll try again. F of 1, I'm going to put it in that first piece, that x piece. So f of 1 is equal to 1. That's kind of the left-hand side. So it's not really f of 1. I'm not loving my notation, but that's what we're going to go with. All right, hang on a second again. All right, I had to reconnect the iPad. So on the left-hand side of x equals 1, I have f of 1 equals 1. To the right of 1, we're going to use that 3. So f of 1 is equal to 3. Now, limit notation, we're going to talk about left and right-hand things and limit notation a little bit better next time. But I should probably do that now, shouldn't I? See, if we're all learning, the best way to do these things here. So the limit, here we go, I like this better, of f of x as x approaches 1 from the left. We haven't discussed left and right hand, but this is not -1, it means 1 from the left. So I'll put this 1 into the first piece is 1. The limit as x approaches 1 from the right, I'm going to use this piece because it's on the right-hand side 1 of f of x is equal to 3. There we go. And we're going to do it again around the 3, and then I'll tell you what these things mean. We'll talk about that a little bit. So this is at x equals 3. So we have the limit as x approaches 3 from the left. Now we're going to look at this piece of f of x is equal to 3. And the limit as x approaches 3 from the right. So now we're dealing with this piece down here because it's x is greater than 3 of f of x. We're going to put this 3 into here. So 2 times 3 is 6. 6 minus 3 is 3. Now, I may have jumped ahead a little bit with the notation, but you are hardworking students. I know that you can handle this. So let's go back and talk about these a little bit. The first one, because these don't match, the left and the right hand limits don't match, this is going to be a jump discontinuity. And over here on this side, because they do match, this is continuous. I spelled continuous there. Now, describe the continuity. Let's go back to the original question. It is not continuous at x equals 1. It's continuous everywhere else. The other thing that you can do with this is graph this in your calculator. or by hand. I know that some of you are experts at graphing piecewise functions in your calculator from pre-calc. You had some pretty awesome pre-calc teachers. If I look at 1 and I look at 3, f of x equals x looks like this. Then here's 3 as a horizontal line, like this. And then 2x minus 3 is a line. You kind of have to pretend where it is, down 3, up 2, right 1. It's going to go like this. So you can see that there's a discontinuity at x equals 1, and it's continuous at 3. It's continuous everywhere else. Okay, so I may have over-explained that one, but I hope you get the idea. Remember, ask me, ask Mrs. Oakes, we're here to help you out. Example 4, for what values of x is f of x discontinuous? This one's a little bit easier to see, and I think you'll be happier with this one. What you got to do is some algebra. Calculus is all about the algebra. You want to factor, so the x squared minus 9, reaching way, way, way back, is difference of squares. This is x plus 3, x minus 3. That denominator factors as well. I've got an x minus 2 and an x minus 3. So you want to cancel out anything that's the same in the numerator and denominator. So we are going to cancel x minus 3. So we are left with x plus 3 over x minus 2. This is the function that's left, and if you graph that, that would be what it looks like. But this piece is important, but what's very, very important is the denominator. When it comes to discontinuities, you're not allowed to divide by 0. We know that doesn't exist. Our calculator says undefined, our teachers say undefined, we can't divide by 0. So anytime you get a 0 in the denominator is when it's not continuous. So that happens at x equals 2 and x equals 3. Those are your discontinuities. Numerator doesn't matter, just the denominator. The numerator matters only in that you want to see where it cancels. So see how the x minus 3 canceled out? That makes it a removable discontinuity. You literally removed it from the problem. So x equals 3 is a removable discontinuity. And then x equals 2, we don't really know what that is. If you graphed it, you would see that it's an infinite discontinuity. Your jump discontinuities most of the time, 90% of the time, come from those piecewise functions. This one's going to be an infinite discontinuity. So there you go. And right now you have access to a graphing device, whether it's Desmos or your calculator, so feel free to use it. Next thing I have is the intermediate value theorem. Intermediate means in the middle. So my intermediate value theorem talks about values in the middle. It states that a continuous function on an interval cannot skip values. That's kind of the English way to put it. So here's the mathy way. If f of x is continuous on a closed interval from a to b, and f of a does not equal f of b, then for every value m between f of a and f of b, there exists at least one value c such that f of c equals m. It's very, very wordy. What are we talking about? Here's A, here's B. They're not the same. What I'm saying is if this is a continuous function, which the one shown is, and I give you a value m, there has to be at least one c that corresponds with that value m somewhere along the graph. And in this particular case, I've got more than one. I've got 3, but there has to be at least one. There's no maximum, but there's a minimum. There has to be at least one. So we use this to prove roots, to show roots. And existence of zeros is kind of a second piece to that. I didn't realize they were right next to each other. If we have f of a and f of b are non-zero and they have opposite sign, then f of x has a 0 in a to b. So what that one means is it has to cross the x-axis someplace. Remember, 0 is where you cross the x-axis. So f of a and f of b, if they've got opposite signs. So let's draw them in here. So here's a, here's b. F of a is down here, it's negative. F of b is up here, it's positive. They've got opposite signs. You have to cross the x-axis somewhere. And in my picture, cross closer to the A. So it's just saying there has to be a 0 somewhere in there. All right, so let's prove f of x equals x squared plus x equals 1. All right, so for example 4, we're discussing intermediate value theorem. We want to prove that f of x equals x squared, nope, x cubed plus x squared equals 1. We're really looking to see that it takes on the value of 1 somewhere. So yes, you could graph that in your calculator and see what's going on with it. But before we had access to graphing calculators all the time, or if we really want to prove it and not just look at a picture of it, we want to see that this function takes on the value of 1. So it's not worded exactly in the question, but here's what we're going to do. We are going to make up some values. I'm going to say that f of 0 is equal to 0 cubed plus 0 squared, which is equal to 0. And then I'm going to say that f of 2 is equal to 2 cubed plus 2 squared. So this is 8 plus 4, so this is 12. So I know that x cubed plus x squared is a continuous function. It's not divided by 0 anywhere. There are no square roots anywhere. It's continuous everywhere. And because I can say for certain that y equals 0 when x equals 0, and y equals 12 when x equals 2, I know for a fact that f of x is equal to 1 somewhere by the intermediate theorem. And that's because I can't skip values between 0 and 12. It's 0 to 12, all the integers, all the decimals, all the fractions, all the way in between. So 1 is between 0 and 12. So the question didn't ask this, but the corresponding x value would have to be somewhere on the interval between 0 and 2. I know it's not equal to 0 or 2 because we said that x equals 0, y equals 0, x equals 2, y equals 12. But the corresponding x value, that solution, is going to be somewhere between 0 and 2. So we've proven that that function equals 1 somewhere. For example 5, we want to prove that sine of x equals 0.3 has at least 1 0. Well, what we could do is say sine of x equals 0.3 has 1 0. We really want to test the function and look for opposite values. So I'm going to subtract that 0.3 to the left. So sine of x minus 0.3 is equal to 0. We want to prove this. So again, we're going to try some values. I am going to say that f of x is the sine of x minus 0.3. Again, you could graph this in your calculator, but if we do this without graphing, I want to find f of 0. So this is sine of 0 minus 0.3. So sine of 0 is 0, 0 minus 0.3 is a negative 0.3. Then I'm going to try out f of pi over 2. So sine of pi over 2 minus 0.3. Remember, we're in radians, so pi over 2 is at the top of the unit circle. Sine of pi over 2 is 1, so this is 1 minus 0.3. This is 0.7. To prove the existence of zeros, we want to know that there are opposite signs. So the first one is negative, the second one is positive. I had to cross the x-axis somewhere. I had to cross the x-axis somewhere. So 0 and negative 0.3 and pi over 2 and 0.7. Somewhere over here, I had to cross the x-axis. So that's my existence of zeros. I know that it's there, which is no problem. I like the next problem. It makes you really think, kind of an AP problem. For what value of k would the following function be continuous? So I have this piecewise function. I know I've got x squared minus 2. That first piece is some kind of parabola that opens up. The second piece is 2x plus 4. That's some kind of line that goes up like this. It is a piecewise function, so if I graph them, I know I'm over here at 1. Here's my parabola piece, x squared minus 2. That's going to have some kind of open circle. Now this k, I'm not sure how high or how low that line goes. So we want to make sure that we get those two pieces close enough to each other so that it's continuous. You want, let me try something here. We want this piece right here to be down here. We want that to be continuous. So that K is going to determine where that happens. So what we need to do is put the 1 into X over here. So f of 1 equals 1 squared minus 2. 1 squared minus 2 is a negative 1. So that y value, I know this happens at negative 1. Now, again, we need this piece to have a y value of negative 1. So we want to figure out what this needs to be down here. So what I'm going to do is say that negative 1 is equal to k times 2x plus 4. But we know what x is. X has to be equal to 1. So negative 1 equals k. 2 times 1 plus 4. Here's my k. 2 plus 4. Negative 1 equals k times 6. K, whoops, 6. K is negative 1/6. So negative 1/6 is the value of k that makes this a continuous function. I like those questions. They make you think outside of the box a little bit and really apply what you know. That is a multiple choice AP style question. So there you go. Good luck. The assignment that's associated with this one is a little bit long. Do the best you can. My BC students, today's Friday. We have the weekend to work through those. Send me questions as they come up and we'll do the best we can to get through them.